Let's go ahead and look at the reactions in the benzylic position now. And remember, the benzylic position is the outside position of the benzene ring, not inside the benzene ring. So here is a little bit of a review again for the nomenclature. Here is benzene. Here is phenyl. Phenyl is when, of course, the benzene ring is connected to something. And then here is benzyl. Benzyl has a CH2 over here, and then anything else could be connected to it. So just as examples, this is bromobenzene. This is benzyl bromide. Remember, this is not phenyl bromide. It's benzyl bromide because of the CH2 over here. This is phenol, the OH directly connected to the benzene ring. And then here is benzyl alcohol where you have a CH2 OH. Okay, so remember the difference between phenyl and benzyl. It's important. So the first reaction we'll talk about is oxidation of benzene. And the oxidation of benzene does not happen inside the ring. It actually happens outside the ring. So these kind of reactions are side chain reactions of the benzene. Okay, and so what happens is that if you have any kind of an alkyl group outside the benzene ring, you can oxidize that using KMnO4, potassium permanganate, or chromic acid, and you will end up getting benzoic acid. Remember, chromic acid and potassium permanganate are really strong oxidizing agents. So we've been using them for a long time, and they will take it all the way to the acid, not to the aldehyde or ketone. Okay, so this is a one-way reaction. So you can have any kind of an alkyl chain, any kind, no matter how long it is, or no matter what functional group there is. Okay, so for example, it can have a double bond or a triple bond or even a ketone. Okay, for that matter, everything will get oxidized to the carboxylic acid. Okay, and this reaction is also known as degradation because really you're doing a whole chain degradation here. The entire chain is gone. All you're left with is a carboxylic acid. So in a way, it's not too bad because if you wanted to make benzoic acid, then this is a good way of making benzoic acid. So oxidation is one reaction. The other reaction you can have is a side chain reaction on benzene. So now what you have is a benzylic carbon. So for example, CH3, okay, which is toluene, can have two kinds of reactions. It can have a radical reaction and it can also have a SN1 or SN2 kind of a reaction. So in case of a radical reaction, you can start with toluene or any other alkyl group, okay, and then you can form a radical at the benzylic position. This radical is highly stabilized by the benzene ring because it undergoes resonance, so it's highly stabilized, which means you can easily do reactions on this carbon. The same thing happens when you have a leaving group on the benzylic carbon. Now remember the leaving group, once it leaves you can have, or depending on what kind of carbon you have here, you can have SN1 or SN2. So in case of SN1, if you have a tertiary carbon here, then you'll form a carbocation like this. And if you have a carbocation, which is tertiary, it will be very stable. If it is stable, it is further stabilized by the benzene ring. A primary carbocation not so, which means that it will undergo SN2 reaction, not SN1. But anyhow, both of these reactions are possible, the free radical types and also the SN1, SN2 type on the side chain of benzene. Let's look at the benzylic halogenation. There are two halogenations which are very common, bromination and chlorination. So the first one to look at here is the bromination, which you can do with bromine in presence of light, or you can also use NBS. The product that you end up getting from bromination is this product, okay, which is the benzylic bromination of an N-propylbenzene. Okay, so this is a long chain that is connected to benzene. However, the only position that reacts is the benzylic position. Now let's look at the same reaction with chlorine. Now with chlorine, you end up getting multiple chlorinations. So here it is not very specific. The chlorine can occur on the primary carbon and the benzylic position and on the secondary carbon over here. So which means anything is possible. So a little comparison between the two reactions is that bromination is a very slow reaction and chlorination is a very fast reaction. You did that back in free radical reactions also. So chlorination will react very fast, and so it doesn't really have any specific place to go to. It will react everywhere, not on the benzene ring though, okay? Anywhere outside the benzene ring. Whereas bromination, on the other hand, is a slow process. And so then it reacts only here at the benzylic position. Now, the slow process also is favored by the fact that once you form a radical at this position, which is the benzylic position, it is then resonance stabilized, okay? And so while the slow reaction is progressing, the benzene ring is also stable. Here, there is no time for the benzene ring to be stable enough because the chlorine reacts very fast. Okay, and so chlorination is not very specific. Now, in this case with bromination, this is a really neat reaction because if you wanted to get bromine at the benzylic position, now you have a way to do it. Okay, so then you can go ahead and do SN2 reactions on this or any other reaction you wanted to do. With chlorination, however, that's not possible. Another reaction that occurs outside the benzene ring is the reduction of the side chain. Okay, and we did two reactions on this, Clemmensen reduction and Wolff-Kishner reduction. If you remember, we did that with the acylation reaction. And so because it's a side reaction, this is kind of a little review also then for you, is that you can still do it. And so here is reduction using Clemmensen, and here is a reduction using Wolff-Kishner. In both cases, you would get a CH2, which means that the carbon is completely reduced. Okay, and so this is also a side chain reduction on the benzene ring. All right. The other side chain reaction that can happen for reduction is the reduction of the nitro group. So you can take a nitro group and then you can make an amine out of it. Okay, so which is NH2. So this reaction is also possible. You can also reduce the benzene ring. However, it's a very difficult kind of a reaction. All right, so it's not easy to do. However, you can. Remember, benzene is very, very stabilized, okay, ring, and so because of its aromaticity and all, it's very hard to reduce. So, which means you have to use hydrogen and whatever the catalyst is, and then you very high pressure and high heat. Okay, and so you can reduce that. You can reduce one bond at a time, okay, like this, and depending on the excess hydrogen, you can keep reducing it to give you completely cyclohexane then, okay? So here you have a conjugated cyclohexane, hexadiene. Here is the non-conjugated version of it, and then of course you have the cyclohexene and going on to cyclohexane. With the hydrogenation, you have to be a little bit careful, okay, because if you have any other functional group in there, that may also get reduced, especially alkenes or alkynes, okay? So if you're doing hydrogenation like this, you have to be careful because everything else that can be reduced by hydrogen will be reduced, okay? So in the previous slide, we just saw that you can use hydrogen to reduce the nitro group also. So if there's a nitro group there, you can reduce that too. So hydrogenation is not really the best way to form cyclohexane. You are much better off buying cyclohexane as cyclohexane. A little bit about the nucleophilic substitution on the benzene ring. Now, benzene ring is highly nucleophilic itself. Okay, the whole section that we talked about where we have electrophilic reactions on the benzene ring is because benzene is the nucleophile. So which means that it's really very, very hard to do SN1 or SN2 reactions on the benzene ring itself. Okay, so it's a very tough process and there are very, very few reactions that you are able to do on the benzene ring, and typically that also not in the lab. Okay, these are some things that are done in the industry where extreme conditions are possible. Usually in the lab, you don't really have those extreme conditions. So for example, one of the industrial way of making phenol is taking chlorobenzene and then treating it with sodium hydroxide and heating it, okay, under pressure. So once you give it under extreme conditions, then the sodium hydroxide, the hydroxide here would be, it's a strong nucleophile. It's just that the benzene is such a nucleophile itself that it does not let SN2 happen on it. So hydroxide, a good nucleophile, then will go ahead and displace the chlorine. The mechanism of the reaction is kind of interesting because the hydroxide does not go for chlorine directly, it actually goes for the hydrogen next to it. Okay, and so once that happens, you end up forming this little intermediate here, which is called benzyne, and which is really very unusual because there's a triple bond along with the two double bond. Okay, so the triple bond makes it the benzyne, and it's a very, very intermittent species, so it will go away very fast, although it has been trapped by using some other reactions, and therefore we know that it exists, except that you can't really isolate it and keep it because it's very unstable. Okay, and so then immediately with the addition of water, you get alcohol. So phenol then can be made industrially this way, but it's not a very good lab synthesis. So again, just a few reactions that you need to know from this little portion is the oxidation of the side chain, which is a KMNO4. Benzylic position reactions, the chlorination, bromination, know which one is more specific than the others. The reductions that we talked about, which is the Wolff-Kishner-Clemmensen on the nitro group, and then the benzene rings, and of course the nucleophilic reaction on benzene. That's about it.